Thanks everyone for joining us here for this workshop. Before we get started on this unadulterated, unapologetic sales pitch for AIDA version 1.0, first a few notes of just planning, general stuff. So I sent you a link to the program. We just slightly adapted the program with respect to today. So what we'll do, I'll start with this generic introduction talk for AIDA 1.0. Then we'll get Oscar, who will tell us something about Python 2, Python 3, based on the work done by Tiziano. We'll have probably we'll arrive somewhere around 4 o'clock. We'll have a coffee break. And then we'll finalize this day with Leopold giving us some step-by-step instructions on how we can get started with migrating our plugins. And then however much time remains, until 6 roughly, we can actually start doing some work. And the rough plan for all the following days is, as a guideline, we'll work between 9 and 6, with lunch from 1 to 2, and coffee breaks at 11 and 4. These are guidelines. I mean, you can do whatever you want, of course, but then we'll be here and working, and so we can ask questions, have discussions, etc. And for now in the program, we have some specific slots reserved for generic discussions. Because what we would like to ask you at the end of tomorrow, Tuesday, when you've already worked for a day and a half with the new code, started migrating, and maybe you've already seen some, encountered some problems or found some things confusing. And so we're going to ask you for like a topic that you would like to maybe discuss or us to go into more detail. And then we can slot this in on, let's say, on Thursday. So, but other than that, we're kind of very open. And if you have questions during this weekend, that's why we're organizing this.
Can you maybe press the button on the microphone, because Jens is saying, or maybe on the one.
On this one?
Yeah. He said he couldn't hear you.
And now, can you hear me? Perfect. All right. So with that out of the way, I think let's get started. So as I said, I will start this with my presentation. When originally I was going to give a presentation with just the backwards incompatible changes and what really had to be done during the migration. But then I realized that this was basically based on the assumption that everybody is already familiar with the new concepts. And since I've been working for a long time and been developing, I realized that this might not necessarily be the case. And so what I decided is to go to a blank slate. Imagine that you're coming from AIDA 0.12 and basically explain what the difference is in 1.0 and mostly what the good parts are. And then after that, once we've done this, then I will give a very short overview in terms of concepts, what the really differences are. Not so much even the migration steps that you have to do, but just the general idea, the concepts that are different. So as an overview, the things that have improved the most and have changed the most is we've improved the command line interface, and specifically we have now a homogeneous and consistent interface for Verde. There's improved tab completion for not just the commands themselves, but also for the parameters, so the flags, the options, and even some of their values. And hopefully these components are now easy to be reused in plugins. So all the validation, you can basically use the exact same components we do in Verde, which should make your life a lot easier. The daemon. Now there's multiple daemons per installation, and there's multiple workers per daemon. We'll see later why that is useful. We've gone to an event-based engine. The old engine was a couple of tasks that were running consecutively and just scanning, polling the database and updating, which we found had problems when you're scaling to high throughput scenarios. And so that's why we implemented an event-based engine, which hopefully should alleviate all this. Part of this is that there's now a clear separation of processes and nodes, which has multiple advantages. But that's a big change, and that's something as a concept we'll have to get used to going from 0.12 to 1.0. But now also it's a lot more scalable, and it's, I dare say, lightning fast. I've done some initial benchmarks myself, and it seems to be pretty good. And finally, now there's a provenance graph implementation that is not broken. How is that a feature, you ask? During the development of AIDA, from the beginning until 0.12, stuff has been added, and not always was everything taken into account. And so really in 0.12, the graph, the provenance graph, the API specifically is broken. Since this is one, if not the core concept of AIDA. This was, of course, a big problem. So we spent quite a bit of time redesigning this, formalizing it, and now making sure everything, we have a clear picture of what the provenance graph is, what rules it obeys, and how it's implemented and how you can use it. And so this is now finished in 1.0. So we'll explain this a little bit. And some direct additional advantages are that now you can determine a level of granularity that you want to inspect the provenance graph in. And querying, if you're looking for specific stuff, allows you to, in a taxonomic way, identify things more clearly. This will all become more clear later on. So with this out of the way, go to the command line interface. What we've done is we've re-implemented Verde on top of the Click library. Click library is a Python-based command line interface building tool that's widely used, widely supported, and is really, really a pleasure to use. And what this gives us, essentially, is that because you define certain components once and you just rename them, so you avoid basically code duplication. And as a result, you have consistent naming and validation of parameters. So if you define a node option to take a node, this will now behave and look the same everywhere without us having to worry about this. These help messages are now automatically generated, so it's impossible for us to forget to update. We update the flag and we update the help string, and then we forget to update the code, the help string. Since this is now automatically dynamically generated, this is no longer a problem. As I said, improved tab completion, and we simplify development for ourselves, which makes development easier, but also for plugin developers who can use these components easy and extend their own. So tab completion. Now, what we already had, we used to have our own home-baked command line interface. But now, and this was already there, but so if you do Verde profile, for example, and you do tab, the subcommands will be auto-completed. But now, there's also options that are completed. So for example, Verde takes, if you start with a dash and do tab, it will auto-complete the available options. And not just that, but also the values. So if we dash p is for a specific profile. In my case, I have two profiles, Django and SQLA. So if you do Verde dash p and do tab, it will show you and autocomplete the profiles. This goes for not all parameters because we have to implement them, but for a big subset, we have already implemented this. And the same goes for arguments. So Verde profile set default takes a profile, tab will show you the profile. So this is very useful. As I said, these click parameter types can also be reused by you as users. So just as an example snippet of how you can build very quickly your own command line scripts. So we start with the shebang for Python, some encoding, and here we import the click parameter. And to create a click command, you should simply make a function and you decorate it with this @click.command. That turns it into a click command. Now we just, in the main, this is the normal way. If you have a top-level Python script, this calls the function. And now, for example, we want a function that takes a node. Is this ever readable for everyone, by the way, the snippet? So this takes a node. Normally, what you would have to do is you would take maybe a PK or a UAID, and you put this in your help string. And then when you come here, you have to validate. So did the user actually specify something? Is it correct type? Now you can just, from AIDA, import this module, the command line params arguments, and you simply do .node, and you set it it's required true. And now this will do everything for you. It will do the automatic help string. It will do the validation for you. It will actually turn the PK, the UID, or the label into a node. So when you get here, you're guaranteed that this node is actually a node instance. The only thing you have to make sure is that the database environment is loaded, and you used to do this with try load dbm or his dbm. Now you can do this with this decorator that you can import from here. Decorators with dbm, and this will automatically load everything. And only when it's needed. So if you just import the script, it won't do it. Only until this file is actually called, the function, it will load it lazily. So the way what this looks like, if we actually call this and we forget to pass our node, it will do the validation automatically and will tell you missing argument node. And again, this will look exactly the same as in any Verde command. So again, this is very consistent. We can pass an ID. In this case, the ID doesn't actually correspond to a node apparently, so raise an error message. If we do find one, it will load the correct node, and you see this is actually a node instance. And And many of these options, there's a lot of predefined. So you can load nodes, computers, codes, profiles. There's a bunch of them. I'll invite you to go explore at some point to see what's already predefined and what you can reuse. And some of them are even easily customizable. For example, options.code will add a flag for a code, but you might want to specify a specific code for a specific entry plugin for your code. So you can override the type by using this and setting the entry point. So now this will not just verify that whatever identifier is passed corresponds to a code, but that also it's configured to run arithmetic.add. So what that looks like, again, if we don't specify it, it will complain. If we specify a code with the wrong entry point type, now this does the automatic validation. And if we add this one is configured with the right one, everything is hunky-dory. So I already mentioned these identifiers. There's this new concept in Verde, or now we've generalized this and made it more well-defined. Often you have to identify a certain, either a node or a computer or a code. And you can do this in AIDA through 3 different types of identifiers. Namely, it's the ID or the PK, the UUID, or a label. And so on the command line, the difficult part is you pass in string information. So you cannot really tell what you intended to be. But we made these things pretty clever, and they will try to infer from the content what it is. So now all these identifiers will all accept IDs, UIDs, or labels across the whole interface. And the way this works, they will first try to interpret it as an ID, sometimes as then as a UID and as a label. So the way this works, if it's an integer, we can just cast it to a PK and it will load it correctly. And you see this is a node, a code with the name add PK15, and this is the UID. And so we can also load it with the full UID. If we pass the UID, it will guess automatically that it's a UID, and you get, again, the same node. But sometimes you can see there might be some ambiguity. You can also use a partial. You don't have to use the whole UID. You can also use a partial part. But sometimes that might lead to ambiguity. Let's say you see here it starts with, the UID starts with 2225. And so you might want to load it by using the partial UID. But the code thinks this is an ID because it's an integer. And so you will see it failed to find it with ID. Oh, this is wrong. I'm sorry. It's supposed to say 2225. But you can always include up to the first dash or the first non-numeric character. And then the code knows that it has to be UID. And then so again, it will find it. Same with label. You can use the label to find it. But however, in this case, add is also hexadecimal valid. And so the code will think that it's a partial UID. So here we'll try to load with UID add, and it won't find it. But then we have a special, in this case, we don't have the built-in UID, the dash character, but we have a specific reserved characters, the exclamation mark. So if you want to enforce the code to interpret it as a label, you just suffix it with an exclamation mark, and it will load the right thing. It's kind of nice. Don't give me UID, bad. It's the label. So that's the command line done with. Then the daemon. As I said originally, each installation of AIDA, each like config folder, if you will, had a single daemon. So you had a daemon user, and all the profiles that were in there used a single daemon. Now, however, you have one daemon per profile. So in your installation, you can have multiple profiles, and each profile will have access to their own daemon. And so now when you do Verde daemon status, it will show you for which profile this is. You can add the -- all flag, and it will show you the status for all the daemons. So in this case, again, I have 2 profiles, Django and SQLA, and they're running in parallel, independently. And you can see this like this. Another big advantage is that by default, each daemon now has a single worker, but you can control the amount of workers. So these workers, we'll get back to this later, this concept, are daemon workers, and they're independent processes. And they can work on specific tasks. And you can add as many as you want. Well, there's a bit of a question how many is, of course, infinite is not going to be possible. But for example, here we have 6 workers, and they're happily working independent from one another. Then the engine. There's a lot of change in the engine. And without going into the specifics of all the technical details, the architecture, one big concept that is new in 1.0, that everything that now runs is a process. And so we typically have now 3 process classes. One you might already be familiar with, because the work chain has already been there since, I think, version 0.8, and has, in that sense, remained unchanged. Then there's the calc job, which will come back later as what used to be the job calculation, but it's quite a big change in how you implement this. And then there's the function processes that you never really implement yourself, but are generated on the fly by the engine automatically. They come with a specific node class. We'll come back to this later, why this is important. But already here you see there's like I did in the introduction, there's a separation between processes and nodes. And then here's what they're used for. So like I said, the calc job used to be the old job calculation. So these are calculations that are performed by external codes, potentially with a scheduler on a remote cluster. The work chain is a process that's used to connect multiple processes, so it can call calc jobs or other work chains or work function calc functions. And then we have 2 decorators, calc function and work function, that turn a Python function, one decorated, into a process on the fly. I'll come to the specifics and how you use them later on. The nice thing about these processes, now everything in AIDA that you can run is homogeneous. They're all the same. Before we had to use a work chain or even legacy workflows, and we had the calc jobs, and they all had their own different specifications. They worked different. They had different states, and they didn't even live in the same database table or even in the same provenance graph. This has now all been homogenized. They all work the same, and so they all have a single process state. And there's 2 types of process state. There's an active state or it's a terminated one. So either it's still active or it's done. And once it's terminated, it's never getting out of that state. And then there's various subtypes, so that it starts its life as a created. Then it will start running if it's picked up by the daemon worker. And then in between, it can be waiting. So it's waiting for another process that it called. And when it's terminated, it can be either finished, which, as far as the engine is concerned, it ran through its execution, everything was fine. If an exception occurred that was not dealt with, it will be accepted. And if the user killed it through the command line or one of its callers killed it, then it will be killed. And so they have a few attributes that make it very easy to query their state. Through the .processState property, you can get this value. Then there's the exit status and exit message, which is a new concept, but it indicates if the exit status is by default 0, that indicates that it was successful. But if you want to indicate that it was unsuccessful, like an error occurred, but not an exception, then you can set this to a non-zero integer, along with a message if you want. It's optional. And then these are shortcuts. So is terminated will turn true if it's any one of these. Is killed if it's literally killed, accepted, etc. And then finished or K are combinations. If it's both finished, and in this case the exit status is 0, and failed is if it's finished but the exit status is non-zero. To launch these things, there's now also one single unique interface. Again, before you had a different way to launch a workflow, you had a different way to start a work chain, you had a different way to launch and start your calculation, your job calc. And now there's 4 functions, launcher functions, that can all do the same, have all the exact same interface. So there's run, run get node, run get pk, and submit. And so if we start with submit, the way this looks, for example, here as an example, I take the arithmetic add calculation, which is a built-in calc job in AIDA. You get it through the calculation factory. And then for the submit function, you can import from aida.engine. And the first argument is the process class. So in this case, it's just an arithmetic add calculation. And then the inputs are passed as keyword arguments. So it takes actually 2 inputs, integer 1, x, and integer 2, y. And so this is the way you pass it. This will send it to the daemon. But you also have the possibility to run it in your local interpreter. So this is what run means. It will, in your shell, if you type it, it will actually execute the whole thing, whatever it is, in the same interpreter. So you won't get control back until the process is finished. Sometimes this is useful. And so as you see, the interface is exactly the same. You just swap out submit for run, and you import it from the same location. This will return the result from the process. And typically, these are the outputs that are output, so a dictionary of the outputs. Sometimes you also want to have the node that represents the process in the database, or the pk of that node. And so then there's the shortcut these utility functions, run, get, node, that work exactly the same as run, but they just, instead of just a result, they give you a tuple with the node and the pk. And as syntactic sugar, there's even a shortcut. If you just import run, these functions are also implemented as attributes. So you can run.getNode, which runs essentially run_getNode. Then there's another bit of syntactic sugar which can be useful, because as I told you here, you pass the inputs as keyword arguments. But now imagine you have a process with a whole long list of arguments. You get a long line, and it gets kind of nasty. But you can also, this is just pure Python, you can define your inputs as a dictionary. This is very useful. So you can put all your inputs in one dictionary, and then you do star inputs. And this star basically expands the dictionary into keyword argument value pairs. So doing this will actually implicitly do this. So this is just syntactic sugar, but it can be very useful. So I already said that if you call submit, it will submit this to the daemon. What actually under the hood, for you to give an idea of what actually happens. So a local runner, this is our a runner, can also be a daemon runner, because if the daemon submits something, we'll do the same thing. The first thing what it will do, it will actually store a node that represents that process in the database. Because the process is actually the thing that runs in memory, and it just represents its state in the database. So if you then interact and ask questions, you're seeing a representation essentially from the database. And that's also how it's represented in the provenance graph. So it does this first. It links up all the inputs that you've given it. And then next, it will close down the process and will send a task to RabbitMQ. I'll come back later what RabbitMQ is. And it basically sends a task, listen, I've just created this process in the database and it needs to be run. You send it to whoever is available to run it. So what happens with those tasks? They come to RabbitMQ. RabbitMQ keeps a queue of all these tasks. So these tasks come in, and he will start handing them out to the daemon workers. And those are the workers that I showed you before that will sign up to RabbitMQ system. I'm running. If you have new tasks, send them over to me. So however many workers you have running, these tasks will be distributed by RabbitMQ to these daemon workers. And they will start running. They will load it from the database, and they will actually start running the process. So this RabbitMQ is a new dependency, if you will. This is a program that implements the AMQP protocol, which is a protocol to send messages between different components in a system. And so in our case, to let the user and the daemon workers communicate between each other, we use RabbitMQ. And the promise of RabbitMQ is that all these tasks that we send, they will persist it to the disk. So if we then shut the computer down, RabbitMQ will guarantee that those tasks are not lost. So if you submit a job, we are guaranteed that it will start once we restart the computer. And so each task is also guaranteed to be delivered. We send it, RabbitMQ will make sure that at some point it will be given to a daemon worker. It will only be given once. So it hands it out to a daemon, and as long as it's with a daemon worker, it won't give it to anybody else. And it will wait until whoever picked the task says that I actually completed it. If not, the daemon dies, RabbitMQ will resend it. So this gives us two things. Efficient communication between multiple workers. So we can actually run multiple processes in parallel. We're no longer dependent on one single process that loads everything that needs to be done and one by one starts working on them, which was causing problems in the original design. And we have a guarantee by RabbitMQ, which is very well maintained and used widely, that it will eventually be executed. Again, we go back to this topic. Everything is a process. And so now if you want to interact with these things, once you've launched the process, if you want to inspect what's going on and how things are going, there's the new command Verde process, which is your one-stop shop for dealing with these things. And so your first entry point will be Verde process list. This will list all the active and terminated processes. So before you had Verde calculation for your calculations, for your workflows, for your legacy workflows, for your work chains. Now everything's here in one place. And they will have the process state. So they have a small symbol, whether they're paused or playing. In this case, they're all playing. But you can also pause these things. Then the actual process state. So these are all waiting for something to happen. And then the process label, so these are work chains. This is a calc job, an old job calculation. And you will have now some process status. So this guy is now waiting for a transport task, is waiting for an update from the scheduler. Verde process status will show you a tree representation of the call stack. So this is mostly interesting for work chains. In this case, this is an example of a PW relaxed work chain. It will show you a tree representation of the call stack. So it called 3 base work chains with which each called a calc function and a calc job. And you can see the PK and their status, etc. This also works for a calc job, but then it's very boring. It's just one line because it doesn't have the capability of calling anyone. The report, which was essentially the old log show. So you get this is for a work chain example. We'll get you, this is for human readable messages that are in a work chain called by do self.report. And this will give you a nested and indented structure of the log essentially that happened. This also works for calc job nodes. If you do a Verde process log show for report for a calc job, it will show you the typical the scheduler error, scheduler output, and any potential error messages. And then you can interact with these processes if they're active. So you can pause them, which can be very useful. It's also used by the engine itself, as I will show later. If you pause them, you can then play them again. And you can kill them. And of course, if the process is already terminated, then those things will give you an error. So about engine robustness, all of this stuff allowed us to implement some, I would say, seemingly small things, but ultimately they might be very useful and very worthwhile. If you remember, if you're in old AIDA, a job calculation might have to interact with the remote cluster, had to upload the files or like submit them or retrieve them. And if there were problems with the SSH connection, the cluster was down or there was internet problems, that operation would fail and would end up in submission failed or retrieval failed. Now this calculation was then lost. It could not continue. Whereas really this was just a temporary problem because it's just a computer problem. And so now instead what happens, there's this exponential backoff. So if this calc job fails to do any of its transport tasks, for example, uploading the files to the remote, querying the scheduler or submitting it to the scheduler or retrieving the files, it will automatically reschedule the same tasks. So okay, try later. And currently these are not configurable, but at some point we'll make these configurable per profile and even per calculation job. And currently the default is that it will retry 5 times, each time waiting twice the amount of time. So sometimes since often these are just connection problems, the problem will correct itself. The daemon will retry and you won't even notice that something has failed. With the additional bonus that even after 5 attempts and it still fails, instead of just accepting process and giving up, it will now put it in pause state. And I'll put a message. So pausing after failed transport task, it tried to retrieve it 5 times and 5 times consecutively it failed. And this will often happen. You submit all your calculations before the weekend on Friday. You come back home, come back to work on Monday, and you see that all these things are paused. Now you check the scheduler and say, there was some maintenance. The cluster was down, but now it's back up. And now you just simply replay all your processes for the process play, and everything continues where it left off. And so for a single calculation, it's not that big of a deal, but if you have a big work chain that has done a lot of work and at the end comes at one job calculation, the last one it needs to do, and that fails, your whole work chain was lost, essentially. And now this no longer happens. So I imagine that this will be a very useful full feature. In addition to this, we had some problems because we've made AIDA so fast now. We've got complaints from CSCS and other people that AIDA was going too fast, was making too many requests. So we actually had to implement some throttling mechanisms, which are actually kind of useful because it will also save you a lot of bandwidth. And one thing, I won't go into many details, but one of them is actually the transport throttling. So instead of every process itself opening a connection whenever it needs to do something, now this will be managed by a single daemon worker, and every process will just ask it for transport. And you can set this interval, a save interval. For my local host, I've set it to 0 because I don't care how often I connect to my local host. But for an SSH, it's by default set to 30. You can configure this yourself per computer. So each computer has maybe a different rate that you want to set it to. And what this essentially, so let's assume we set this to 30. What this guarantees that for each daemon worker, it will at most open an SSH connection only every 30 seconds. And then all the processes that need to do their stuff, they will get this transport and they will all use the same transport. So you don't have open and closing, which is important because if you start running, like for my project, I was running 20,000 processes an hour. If you every hour open 20,000 SSH connections to a machine, that's going to be a problem. So this is now built in and configurable per computer. But that's not enough. But again, if you have so many processes, and even if you open only one SSH connection, if you use that same SSH connection to then call the scheduler for a status 30,000 times, the scheduler is also not going to be happy. So we also have, on top of this, a scheduler throttling mechanism. That is the same way you can set this per computer. So you can. This is a snippet from Verde shell to show how it's done. You can load the specific computer through the ORM, and then there's this minimum job poll interval attribute. You can see here it's set to 30 seconds. So what this means that also within per daemon worker, the scheduler will only be queried for the job state every 30 seconds. So again, with all the processes that need to update their state, instead of doing it themselves, they will just ask the daemon worker, listen, I need to update my state, can you do it for me? And the daemon worker will make sure that it will not exceed this rate. And so you can set it easily with set minimum job poll interval.
And the default is 30 seconds again.
Sorry?
The default is 30 seconds.
Default 30 seconds, but this was I have to admit here that this was added relatively recently, and we're still debugging this, and also we'll make it at some point easier to configure this potentially, because now there's a bit of a discrepancy, and we'll start to document these things. But they're already in place, and this is very important if you're working with lots of processes and clusters, because they're not going to be happy. All right. Then finally, the provenance redesign. As I said in the introduction, as we've been developing AIDA, at some point we introduced things and we really didn't oversee some of the consequences, and the provenance design as it was in 0.12 is broken. So we spent a lot of time redesigning, rethinking about this, and finally found a solution, and this is now implemented. There's now two very clear, distinct types of processes. So I already thought everything that runs as a process, we've seen some examples. And so we have calculations and workflow type processes. The thing that sets them apart is that calculations can create new data. We'll see soon what this means. And workflows can call other processes, and they can only return existing data. So workflows don't have the capacity to create new data. So there's a very important distinction, but this will help us reason and about the provenance graph, and this made it possible to create a clear implementation. So easiest just to give an example. So in AIDA, you're already familiar with the decorators potentially if you work with an early version. So the most simple example is to how we create a process by, let's take this example. We have two functions, an add and multiply, that adds two integers and multiplies two integers, and we can call them like this in Python. To transform this into a process in AIDA, we use a simple function called calc function, which is a decorator, and you just decorate these functions. And now this will automatically turn this into a process by the engine. The only thing you have to do is if you call it, you'll use AIDA, you're all familiar with this, you have to make sure that the inputs are storable. So instead of passing plain Python integers, you pass them wrapped into an int, which is a subclass of node, which allows them to be stored as inputs in the database. And so what this then will do, will generate this provenance graph in the database. So we'll see here, these are the two inputs that were given to add. Add is a calculation type process, as the word calc function indicates. And so it creates a new piece of data, namely the sum. Then together with the sum and this third integer, we pass this to multiply, another calc function, which in turn creates the final result. To show the difference between the calculation process and the workflow process, here we don't really see the flow, like how these were called. I mean, we can see that they were called in succession, but you can imagine that this was called like a week ago, this function. We stopped, went on a holiday, we came back, and we just simply took this integer and just decided to pass it to this function. There's no history of who called what and in what sequence in that sense. And this is what workflow-like processes are designed for in AIDA. So if we take this example, but now we add a work function. So notice the distinction. This is a calc function, so this makes a calculation-like process. As a work function, this makes a workflow-like process. And we call it add and multiply, which now takes 3 integers. It will call the calc function add, and then we'll call multiply with the result, and it will return a product. And so now if we call this, the provenance graph looks a little different. So we see our 3 input nodes now. Now is this new node. This is the workflow, the work function node. And you can see that these inputs are passed into the work function. There's an explicit call link. This work function called this add calc function, which happens at this line. And this will create the data. It then subsequently calls the multiply calc function, which then finally produces the final result. And also you see here now a return link. So this work function returned this result. Now why is this nice? Because this is a simple example, but you can imagine that if we start writing more complex work chains, you get hugely complex work chains with a lot of provenance. And sometimes you're not interested in all the nitty-gritty details. Sometimes you just want to see from a top level, I wanted to add and multiply. You want to just see this. I want to see the inputs and I see the output. And so now, because we have formalized these rules, we can very easily follow the different types of links and the different types of nodes, which allows us very easy to collapse, if you will, the provenance graph. So in this case, we all follow the logical provenance. So we follow the inputs that are passed to the workflow process and the return link. There's a big distinction here that this is a different type of link. It's a return link because this data was not created by the workflow, by the work function, but it was actually created by one of the calc functions that it called. But at the same time, we can also decide to ignore this additional workflow, the logical provenance, and we just want to see the old one. So if you notice that if we just ignore all the workflow-like links, the call links, the return links, and these input links in the node, we'll go back to the original example. So your data provenance is not lost. It's simply some information that's added on top. Some of you might already be familiar with work chains. They're like work functions, but they have a lot of nice bonuses and features that I won't go into detail because we'll leave that for the tutorial in the end of May. But essentially, this is a different way of defining them. And with an outline, they define their steps. But the nice thing is that the progress is saved between these checkpoints. So a work function is nice for simple things, but if they get interrupted, you lose all your progress halfway through the function. But by splitting it up and putting it in a work chain, the progress of the process will be saved in between, and it will actually create exactly the same. This example will create this exact same provenance. It's just a different symbol for the work chain compared to the workflow, as you can see here. I decided not to go into details on the new stuff, the new features in the work chain, because that would be too much. But if you're already later through the week advancing quite well, and you have some questions about work chains, new features, by all means, feel free to ask. So, to summarize the new provenance graph, we have, in the documentation that I've updated, I'll explain all this stuff with a lot of these graphs to explain the concepts, and I will use this legenda, if you will. So the pink ones are the calculation-like processes that can only create data. The orange ones are the workflow-like that can call other processes and can return data, and then we have the old-school data. And so these are the typical the links that you see. In the code, if you ever need to work with this, there's a distinction between inputs to a calc or to a work. They're called input work, input calc. Collectively, we'll refer to those as input links. But if you want, you can address them specifically. And then the same with the call links. There's a call work and call calc. And then there's the old create and return links that were already there. To make all this possible, we also had to redefine the ORM. So there's a new ORM hierarchy in the ORM class. So at the top, we have our node. Every entity in the provenance graph is a node. And so they're split in 2 categories. We have the process node and a data node. So data are passed into the process node, and they can create or return new data. These are then split in workflow node and calculation node. This is to make clear the distinction between the calculation-like processes and the workflow-like processes. And finally, these are then split in these 2 types. And the important thing to remember is that only these classes will actually end up in the database, in instances of these. But these are very useful to reference them. For example, if you want to query for not just only work chains or only calc jobs, but you want to query for any process in the database, you can just look for process nodes because they will match all of them. Or if you only want workflow-like processes, you can look for workflow nodes because they will match both of these. So they're more like a grouping, a taxonomy class. And the rules for the links are as follows. So links that go from data to a calculation node are input calc. From data to a workflow node are input work. From calculation node to data is create. This is what was already there since the beginning. This is what caused the problems initially when we added this and we broke acyclicity. So from workflows to data is return. And then finally, there's the call links from workflow to calc or from workflow to other workflows. Then, so these are the new things, and it's not everything, it's a subset. But now to give you a small overview of what changed practically and how you, the things that you might already know in code. This will be relatively short. And if you want to have a full summary of backwards incompatible changes, it's being curated and maintained on the wiki of aiida-core. I will send, after the talk, I will send these slides to everyone, so you have the link. The reason is that these are on the wiki because as we go along, we might find other things that we forgot about, and it would be nice to update them. That's why we kept it as a wiki and not static on the documentation. Then the biggest thing that really probably most of the time will be spent on is this job calculation that has been replaced by the calc job. And this is difficult to, it's not just naming changes, but it's really a different way of thinking about them. And so since that is the biggest part, we wrote a step-by-step plugin migration together with Leopold and Sasha. And that's also on the wiki. So that will really do you step-by-step, explain the changes and things you have to do. Then the module hierarchy. This is the snapshot of just after we released the beta. And so these are the second level packages within the aiida-core package. And it's too difficult to mention everything, but in the big picture is that Aida utils has been merged into Aida common. And so not all the files they've been spread a bit, so that's a bit unfortunate. Aida scheduler has been renamed to plural. Transport has been made plural, and Aida work is now Aida engine. Again, for a complete list, we can go to no.
Maybe mention also that they have some specific meaning. So maybe.
Yeah, exactly. But that's on the following slide. So the idea is also due to this reorganization that ideally, I mean, Aida has a very deep nested structure just for us developers to organize the code. But as users, we don't necessarily want you to have to delve into all the hierarchy. And so what we aim to do is that for users, the public API should always be importable from a second level package. That's going to say you do Aida dot and then a package. And then whatever you need or should have to import will be importable from there. So for example, the data class, you can import directly from aida.orm. Alternatively, what you can do is you import the whole package and you can access it from this way. Now, it's impossible for us to block other things, so you can always, through ORM, import other stuff. We've already, in the module init packages, we explicitly mark what should be bubbled up and what should be exposed on the top level. But for completeness, we maintain a list on the GitHub wiki of all the classes, methods, and functions that we intend for people to be used. And why is this important? Because whatever we include in this list, we from now on will guarantee that if we change it in any way, ideally, first off, we'll try not to because these are supposed to be stable. But if we really, really have to, then we consider these as public interfaces and we will go through the proper normal routes. So if we make it backwards incompatible changes, we'll up the major version, we'll make a proper deprecation path, etc. Long story short, anything that you can import from this list, you can use safely. You can use it knowing that we won't change it willy-nilly and it will break your code. On the flip side, anything that is hidden further, use at your own risk. I mean, you can use it, it's there, but we might move it, change it, whatever, so we won't give any guarantees there. Then the ORM has changed a lot for the way it's implemented, which makes it the implementation mostly for developers a lot nicer, but also for users it's a bit different and also quite nice. So now all the ORM entities can be directly imported from ORM, and this is how you construct them. I mean, not much has changed there. but now there's this concept of a collection. So here we create a single computer, but then in your database there will be multiple computers, and you can access this collection of computers through the objects property of this class. So you do dot objects will give you a collection of computers, or a representation of those. And so those will have certain methods, for example, get. So to get a computer, you go through the objects collection, you call get, and then in this case with, for example, name. Could have done with host, because name is the unique identifier. You could do pk UUID. There's also a shortcut on the class in the case of get. So you just do oram.computer.get. But the collection has other useful things. For example, .all will get you all the computers. You can find multiple instances with filter. So you can do .find and then pass filters, just as you would do in the query builder. This actually passes, in the implementation, passes through to the query builder. And you can also, if it's implemented, everything is implemented, you can delete certain instances. So this is now also for all ORM entities. This is a single unified way of interacting with those, creating those, and getting them. Then the final big change is the repository. This is in preparation of a big change that we expect to make in the near future. Currently, the repository of a node is essentially a place on your local file system. And so the interface was also designed to reflect this. I mean, you could get from the folder which represented the node's repository, you could get the absolute path. You could get the absolute path from a file within it, or you can add a path from a file system. But in the future, we're going to go to a repository that no longer necessarily lives on your local file system. It might be, for example, a remote file system, or even an object store. So then a local file, absolute file path doesn't make any sense. Or even we want to give the option to pack all the files from a certain node in a tar archive, or even zip it. And also then you cannot directly get an absolute path. So this hasn't been implemented, this change, but since we are releasing 1.0 and want to keep the API consistent from now, we already prepared for this change. And so the new interface, if you want to do anything with the repository of the node, instead of folder, you go to the .repository property, which gives you a representation of its repository. And it has a new set of methods to interact with the objects that live within it. So to see what's in there, you can do list objects, or that will give you a tuple. Or if you're just interested in the names, you can list object names. These are the objects to get them. So this will get the actual content. This will get the representation of the object. And this will give you a file handle. And then you can use it as any, like if you do with open. You can store new objects. So you can put it from a directory locally, or you can put it from a local file, or you can put it from a file handle that you've opened. And then there's ways to delete it. So our hope is that with this new interface, when we then move to the new repository implementation, nothing will change in the API, and we won't have to break anything, and everything will just work. So but this is a big change, that something to take into account. So that was everything. So usual acknowledgements. Thanks to the entire AIDA team and all the people, and you guys, of course, with all the plugin work that you've been doing. So with that, I'd like to end and open the floor for questions, if there are any.